This demonstration video will introduce the PN or intra-pair skew evaluation solution of the MP1900A. As an introduction, let's look at high-speed digital interfaces and how intra-pair skew should be considered in system design. The amount of data processing is increasing due to the widespread use of AI in a wide range of industries. As a result, the performance of high-speed digital interfaces such as PCI Express, USB, DDR, and Ethernet also continues to evolve rapidly. For the examples in this video, let's use the PCI Express Gen 6 standard, which has a 32 gigabaud PAM4 signal, translating to a unit interval of 31.25 picoseconds. Next, let's talk about intra-pair skew basics. Intra-pair skew is defined as the time delay between two signals in a differential interface. This is illustrated in the figure. If the intra-pair skew is significantly comparable to the unit interval, it may be identified at the receiver side as a bit error. Since the unit interval becomes smaller as the transmission speed increases, the effects of intra-pair skew will be more pronounced at higher data rates. A concrete example of the effect of intra-pair skew in the time domain can be seen in the figure. When skew is 0 UI, the resulting differential signal maintains the shape of the positive signal. As skew increases, the differential signal is degraded. This effect becomes even more impactful in PAM4 due to the smaller eye size. In the frequency domain, intra-pair skew causes dips in the FFT graph. This effect is more prominent when using a differential trace. In this PCI Express Gen 6 example, at plus 500 mili-UI, a steep dip at the Nyquist frequency of 16 GHz can be observed. This results in a maximum difference of about 8 dB when compared to 0 UI skew. This clip shows how the FFT graph and the eye diagram behave when intra-pair skew is swept from plus 500 mili-UI to minus 500 mili-UI. Considering intra-pair skew in system design creates some challenges. In the context of high-speed data interfaces, a positive and negative length difference of a few millimeters in both the design of the printed circuit board and the coaxial cables can introduce intra-pair skew and cause bit errors. Other factors to consider are impedance mismatch, bending in the physical cables which can occur in server switches with hundreds of cable connections, manufacturing variation, and the temperature environment. As for evaluation, aside from testing the negative effects of skew, another use case is to measure the range of skew tolerance in cables or DUTs. Even with the importance of considering skew, evaluation challenges still remain. Theoretical simulation can be done, but existing methods of injecting skew to an actual physical system have limited capability or are not granular enough. To provide a solution to these challenges, a novel and reliable method using the MP1900A can be used to evaluate intra-pair skew. In this solution, two PPGs will be used, as seen in the following configuration. These transmitters should be clock and jitter synchronized but independently controlled by phase. This synchronization can be done using the multi-channel calibration function. Make the connections as seen in the diagram. After setting up the modules, start the MP1900A software and select Expert BERT. Then, click on Menu and initialize the application. In the Modules and Boxes tab, click on Combination Setting. Select Channel Synchronization. You will then be prompted to start multi-channel calibration. Click on Yes. Click on the next buttons to proceed. and then wait for the calibration to finish. This message will be shown if the calibration is successful. To generate skew delay, it is introduced by a delay block inside each PPG. This can be dialed in either the positive or negative direction as needed. For the differential signal generation, set the second PPG to negative logic. The PPG to positive data output will serve as the negative component of the differential signal. The unused data outputs should be terminated with 50 ohms or connected to a scope. Optionally, the skewed signal can be passed through the noise generator. This will require a dual mainframe setup. In the example test for this video, we will measure the effect of intra-pair skew on bit error measurements. For PCI Express Gen 6, connect the DUT output to the redriver input. Now, let's see how these settings will look like on the MP1900A. After multi-channel calibration, first select the jitter module and set the clock source to the synthesizer, then click on the miscellaneous 2 tabs of the PPG modules and set the clock source to the jitter module. This will enable the convenient selection of different data rates. On the Output tab, set the desired amplitude for the PPG modules and enable AC on. The intra-pair skew will be adjusted through the delay setting of the second PPG. On the Emphasis tab, turn manual setting to on and set the desired preset or specific cursors. Next, on the Pattern tab, select the desired test pattern. Then set the MSB and LSB logic of the second PPG to negative. We can now inject variable intra-pair skew into a physical system. For a test example, let's measure the BER in PCI Express Gen 6 while sweeping intra-pair skew. In this setup, the effect of skew on the signal before and after an ISI channel is observed. Before the ISI channel, the positive and the inverted negative signal are symmetrical. On the other hand, after the ISI channel, asymmetrical distortion is observed within the differential pair. This distortion can also be seen in the eye diagram. The test setup and the observed effects of skew are summarized in this figure. Let's look at the results and findings of this test. First, a test without impairments, like jitter, noise, or crosstalk was performed. For a PRBS 31 pattern with no gray coding, 30 dB loss channel, and a baseline BER of about 4E-8, the resulting intra-pair skew versus BER is shown in the figure. An increase of 200 mili-UI in intra-pair skew translates to about 1 order of magnitude impact in the BER measurement. This degradation slope gets steeper as more skew is introduced. With SJ injection and PCIe Gen 6 modified compliance pattern, the results are shown in this figure. Adding SJ pulls the baseline BER higher. The tails of the bathtub remain steep in slope. With the same pattern, this time injecting DMI instead of SJ, it can be observed that about 5 MV DMI raises the baseline BER 1 order of magnitude at 0 skew. Varying patterns was also tested. Bit pattern sensitivity can have some impact to BER. Once skew is added, further BER degradation occurs. Generally, the higher order PRBS, the higher the BER. Finally, let's summarize the points discussed. Along with AI applications, high-speed digital interfaces also evolve rapidly. As data rates increase, the unit intervals become shorter and more susceptible to bit errors. Intra-pair skew is an important factor to consider in system design. Its negative effects can be seen in time and frequency domains. Due to the reduced eye size, PAM4 is more sensitive to intra-pair skew compared to NRZ signaling. This distortion due to skew can be readily observed on scope captures. Existing evaluation methods have limited capability or are not granular enough. A novel method for measuring granular intra-pair skew was presented. Dual transmitters on the BERT are used for single-ended control of the phase of the signals within the differential pair. Results show that intra-pair skew can have quantifiable impact to BER margins on PCI at 64 gigatransfers per second, even without any additional impairments. Skew BER is additive to SJ and DMI stress. This concludes the demonstration video. Thank you for watching.